Hey Calc 2 friends, welcome to Chapter 12, Vectors in the Geometry of Space. Our first section is 12.1, Three-Dimensional Coordinate Systems. This is, just to give you a heads up, we typically start Calculus 3 in Chapter 12, so we're going to just touch on it a little bit in end of Calculus 2, so that when you start Calc 3, this isn't totally foreign for you. We're just going to skim the surface. We're not going to go into too much detail, so if you do the reading like you're supposed to, there's going to be much more information in there than I'm going to cover in the lectures or that you're going to be held responsible for. So just make sure you focus on your to-dos, and yeah, you should be good. All right, as a friendly reminder, in 2 dimensions, we represent a point with an ordered pair. So if we have the ordered, the point AB, that means we went over A units on the x-axis, and we went up B units on the y-axis, right? Well, in 3 dimensions, we use ordered triples. So now here's where things get a little crazy. How to identify axes. Typically, when we have a 3-dimensional coordinate system, the axis that goes up and down is now going to become our z-axis. We still have the origin right here. It's now the ordered triple 0, 0, 0. If we go up above that point, that's the positive z-axis. That would be the negative z-axis down there. Now, if we were looking at this and this was coming out towards us, that's typically the x-axis coming out towards us. This would be the negative x-axis going away from us. And then left and right, we would have the y-axis. So positive y-axis to our right, negative y-axis to our left. Commonly, you'll see this. Teachers will use this. They'll use what we call the right-hand rule. So if you point your right finger somewhere, your thumb up and your middle finger makes a 90-degree angle with your pointer finger, and your pointer finger would be the x-axis, this would be the y-axis, and this would be the z-axis, okay? So that's what they're doing there. In 2 dimensions, we only have 1 plane. We have the xy plane. In 3 dimensions, we actually have 3 planes. So imagine this was a room, and this was the corner of the room, and we're standing in this room right here. And if we went to the left a little bit, would be in the next room. If we went through the wall, would be in the right room, and this would be the room below us. Well, if we eliminate the y-axis, what's remaining is the xz plane. If we eliminate the x-axis, we just have that back wall, which would be the yz plane. And if we eliminate the, let me see, x-axis, y-axis, the z-axis, we would have, just did I already say that one? YZ plane. If we eliminate the x, we would have the back wall, which is the YZ plane. If we eliminated the y-axis, we would have one of the side walls, or the XZ plane. So locating points in space can be a little tricky when you try to do it in 2 dimensions, because it's kind of like a bubble floating around in the room. So just like when we have 2 coordinates, x is the first, y is the second. Here, x is still the first, y is the second, and z will be the third. So we just go in alphabetical order. If A is positive, we move in the positive direction on the x-axis. If A was negative, we'd move in the negative direction. Same with Y and Z. So here's a little example where A, B, and Z just happen to all be positive. We start at the origin. We go A units out in the x direction. And then we either go left or right B units, depending on the sign of B. And then we either go up or down C units. And then this would be the point floating in space. So graphing these guys can be a little tricky. So let's plot these 2 points in 3 dimensions. If you're really ambitious, you can Google 3-dimensional graph paper. That's what I have printed out here. It helps a little bit. Sometimes it's still a little tricky. Let's try to find the point 5, 3, 10 in our 3-dimensional graph paper here. And I'm going to do my best, right? So this says I'm going to go 5 units. Whoa, I have my house. I'm going to go 5 units out. So I'm going to start on my positive x-axis, and I'm going to go 1, 2, 3, 4, 5 units out. So I went 5 this way. Now notice these lines that are parallel to the x-axis, that's going to be how we're going to travel in the y direction. So I'm going to go 3 units in the positive y direction. So I'm right here right now, and I'm going to go 1, 2, 3. So I'm right here right now. I went over 5 and out 3. Now I'm going to go up 10 units. So this is where it gets a little tricky. 1, 2, 3, 4, 5, 6, 8, 9, 10 right here. So there is my final ending point. So again, keep in mind what we did is we went out 5. We went 5 this way, and we went over 3, and then we went up 10 to get at that point right there. That's my final point, P. Right. So just be careful if you have negative numbers in there. So this is going to say we're going to start at the origin, but we're going to go -2 units on the x-axis. So we're going to go back 2. right to there. Then we're going to go -4 units in the y direction. So now I'm going to go 1, 2, oops, I guess I shouldn't have really done that one, 3, 4. And then we're going to go up 10 again, so it's going to get me away from this point. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be like somewhere up here. So that would be the point Q, right? So what we did this time is we moved 2 in the negative x direction, and then we went back 4 in the y direction, and then we went up 10 units. All right, so have fun trying to plot some of those points. So there's a lot of similarities between what goes on in 2 dimensions and what goes on in 3 dimensions. Just a friendly reminder, if you're given 2 points in space, we can find the distance between those 2 points using the Pythagorean theorem, and we get the template or the distance formula to just be the difference in the y coordinates squared plus the difference the difference in the x coordinates squared plus the difference in the y coordinates squared. So similarly, in 3 dimensions, the distance formula is very similar. We just have to add the distance between the z coordinates. So the distance between 2 points in space is the difference between the x coordinates squared plus the difference between the y coordinates squared plus the distance between the z coordinates squared. That shouldn't be too hard to remember. Now in 2 dimensions, when we graph things, we get curves. In 3 dimensions, we get surfaces. If we look at the surface of a ball or a sphere, we can use this distance formula to derive the equation of the sphere. So let A, B, C be the center of a sphere, and X, Y, Z be any point, an equal distance R from the center. Well, then R is equal to the distance between all these points X, Y, Z and that fixed point A, B, C. So it's the difference in the x coordinates, x minus a squared plus y minus b squared plus z minus c squared. We don't typically write it like that. We'll usually square both sides just like we do in 2-dimensional equations of circles. Ooh, I don't know why I'm writing so big. Should be minus, big chunky minus sign, right? So r squared is, well, notice if we just take away this third term, that's just the equation of a circle in 2 dimensions with center AB and radius r. So all we did is added on this little extra term z minus c at the end. That's z minus c. Sorry. So again, in 2 dimensions, the graph is just the curve. In 3 dimensions, it's important to understand that it's just the surface of what we're drawing. So if we look at x squared plus y squared plus z squared equals 9, this is a sphere with center at the origin, right? If we took that away, you would recognize it as a circle with the center at the origin. This is just a sphere, and with radius 3. So it's everything on the outside of this ball, nothing that's going on inside, just on the outside. We have equals. If we had less than or equal to, it would be the whole entire ball. It'd be all solid. So it's just all the points on the surface here. So again, lots of similarities. If we were in 2 dimensions and we looked at the graph of the line x equals 3, it would just be the vertical line. Well, lines in 3 dimensions are now planes. And I know this is really tricky to see, but this is the graph of the plane y equals 3. If you notice right here where there's sort of a change in the color, that's where y equals 3. And this whole plane goes on forever. It's like one of the walls. So every point on here, x and y could be anything, but y is always going to take on the value of 3. If it was x equals 3, it would be a front to back. If it was z equals 3, it would be a horizontal plane. So just another couple more cool graphs that I could find pictures of. Z equals 1 over x squared plus y squared. This turns out to be this cute little funnel. And again, it's only all the points on the surface of the funnel. Z equals the square root of x squared plus y squared would give us the cone. So all the points on the outside of the cone. Right, so as far as 12.1, read through it, just get a feeling on how 3 dimensions behaves, recognize the similarities between R1 and R2, and have fun poking around. See ya.